and you're good to go.
Great. Thanks, Kelly, and morning, everybody, and welcome to the third Rare Research seminar that we're able to hold. Apologies for getting on 1 minute a little bit later because load shedding here in Foy's is manic this morning. But welcome, and I'm privileged to introduce to you today Professor Chris Vorster, and I think it's very timeliest that we're hosting this seminar today since we're in the midst of Newborn Screening Awareness Month. So just to introduce a little bit more about Chris, he has started out life as a medical doctor, and then he specialized in chemical pathology. He's worked in the private healthcare sector for several years before joining the Northwest University in Poch in 2010, where he is currently the director of the Center for Human Metabolomics, which is both a research and commercial entity at the Northwest University, which aims to establish sophisticated metabolomics infrastructure and expertise in South Africa. His role in this, in the capacity that he oversees is the National Metabolomics Platform, which is established by the Technology Innovation of South Africa. He oversees diagnostic services for inherited metabolic diseases and newborn screening, as well as several national and international contract research projects and the newly established Rare Diseases Biobank. He also works as a pathologist and interprets and signs out lab reports on a daily basis. And his own research interests are in inherited metabolic diseases, small molecule method development, and nanodiagnostics. And with that, I'm going to hand over to Chris. And if you have questions that come up during the talk, please drop them in the Q&A so we can go through the questions and some discussion at the end. There's also a chat box if you just want to say hi and say who you are and where you're joining us from today. So without further ado, over to you, Chris. Thanks.
Thank you, Ellen. And thank you for the opportunity to present during September, which, like you said, is Rare Diseases Month. My talk is going to be a little bit broader than newborn screening, just because there's a lot of developments in South Africa at the moment. Potentially, we will move towards a screening program in the near future, and I'd just like to discuss this from a couple of angles. Yes, so okay, I think let's start off with that. I'm going to take you through a bit of the history of newborn screening, the current state, and then just some of the challenges. It's not going to be heavy listening. It's more just meant to be informative, create awareness and so on, and also to highlight some of the opportunities that I think may be available to clinicians and scientists within the field of newborn screening. Okay, so not quite the beginning of newborn screening, but certainly the beginning of inborn errors of metabolism was Sir Archibald Garrod, who is credited to have discovered the field. And in 1902, he published this paper, The Incidence of Alkaptonuria, a study of chemical individuality, in the Lancet. Now, it's an amazing paper to read, and the discoveries that he made is actually astounding. So the first thing that he did was that he isolated and identified homogentisate from the urine of these patients. And he did this through a series of precipitation methods, and then by establishing the boiling point of the compound of interest. He also coined this phrase chemical individuality, which he described as missing or false step in chemical pathways. Now, keep in mind that at the time, genes were not discovered just yet. So you could substitute the word chemical individuality with genes, and then he would have discovered genes as well. He was the first to link the inheritance law of Mendel to humans. So these alkaptonuria patients were described to be autosomal recessively inherited. He also realized the importance of consanguinity in alkaptonuria patients, and then in inborn errors of metabolism in general. And he described concepts like disease fluctuation, age of onset, and disease penetrance, which is things that we still discuss very regularly up to today. I'd like to just read you a small section from his paper. He says, "There's no reason to suppose that mere consanguinity of parents can originate such a condition as alkaptonuria in their offspring, and we must rather seek an explanation in some peculiarity of the parents, which may remain latent for generations, but which has the best chance of asserting itself in the offspring of the union of two members of a family in which it is transmitted. So very, very lovely description of autosomal recessive inheritance. Okay, then 30 years later, more than 30 years, Ashbourne-Foiling described phenylketonuria in this paper that was published in 1938, which unfortunately is in Dutch, in German. Apparently, he did publish in English, but apparently he was influenced by Krebs, who described the citric acid cycle and the urea cycle. And he thought to attract a wider audience, he decided to rather publish in German. And anyway, in this paper, he describes the discovery of phenylpyruvic acid in 2 patients that was later then confirmed to have phenylketonuria. And he described in some detail the clinical presentation, including intellectual disability, the fair complexion, eczema, and spastic gait. He was quite a critical clinician, so he was uncertain whether this was an incidental finding, so he proceeded to screen some 400 patients from institution in Oslo and around, and he discovered 8 more cases of high phenylpyruvic acid excretion. And based on this, he then concluded that this was in fact a marker of the disease. He also later described the phenylalanine loading test to screen for carrier status. And the story goes that he did the test on himself, and then it turned out that he was a carrier. But at the time, phenylalanine, you couldn't buy chiral pure L-phenylalanine. So he had a mixture of D and L-phenylalanine. And because of bacterial degradation, his test was positive. So later on, he did manage to source L-phenylalanine, and then he could then conclude that he was indeed not a carrier. So he was also a clinician that experimented on himself. I don't think that's out of the ordinary. I must perhaps just mention briefly with regards to Archibald Garrod that he was described to have very, very poor bedside manners. And he was much more interested in urine than in patients. So he was perhaps also the first chemical pathologist. And he had lots of frustrations as well, patients that were lost to follow-up and so on. So it doesn't seem like the things that we are grappling with is all that new. And anyway, from a publication on the work of Foiling, I just want to read you a few sentences. So it says that Borgny and Harry Egeland lived in Oslo and were married in 1923. They eventually begot 2 children, both of who developed mental retardation. Skip a couple of sentences. In an attempt to explain and potentially treat their children's conditions, the Egelands had sought the opinions of numerous doctors and medical specialists, but to no avail. They also tried herbal treatment and consulted a psychic healer. At one point, young Dag was admitted to Children's Hospital in Oslo for a thorough exam. None of these inquiries yielded an explanation for the children's condition. To test for ketones, a solution of aqueous ferric chloride is added to urine. Typically, no ketones are present and the mixture turns red-brown. If ketones are present, the mixture turns purple or burgundy. Mixing ferric chloride with the urine of Egeland children resulted in neither of these reactions. Instead, the urine immediately turned dark green and then faded in color after a few minutes. So this was the observation that he made, and from there on, he went to isolate and identify phenylpyruvic acids in these children. Okay, then skip a couple of years to 1953, the work of Higmans, Gerard, and Bickel. They were the first to describe the utility of a low phenylalanine diet in PKU patients. And they could show that the neurological effects of the disease could be decreased or limited by providing these patients with a low phenylalanine diet. So this then created a situation where it was known at the time that the earlier you would intervene with a low phenylalanine diet, the better the outcome of these children would be. But at the time, there wasn't a sensitive test to test for PKU. So the ferric chloride test was used, and it isn't really sensitive. So the disease needs to be fairly advanced before you can detect it in such a way. So then came my personal favorite, Robert Guthrie. So he was a clinician and he also had a PhD in bacteriology, which I think was quite useful for his career. So he himself didn't actually have a child that had phenylketonuria, but his second son was mentally handicapped. He did have a niece, though, that was diagnosed with phenylketonuria at 15 months, and this motivated him to develop the bacterial inhibition assay. So he developed this between 1958 and 1960, and then started to screen children in 1961 using what is now known as the Guthrie card and the bacterial inhibition assay. And it wasn't a smooth ride. So again, I just want to read you a couple of sentences from a paper on the work of Robert Guthrie. So it says, by late 1962, over 100,000 newborn tests has been performed, and all of the laboratories reported that the test worked very well. Guthrie believed that this information was sufficient evidence for publishing the validity of his tests to identify PKU by newborn screening. He also knew that for screening to be accepted by the medical community, a peer-reviewed publication would be necessary. So he prepared a manuscript and submitted it to a leading pediatric journal, but it was rejected. Shortly thereafter, he discovered an article in this journal reporting that a comparison of phenylalanine levels in serum measured by a quantitative method and in filter paper blood specimen measured by the bacterial inhibition assay indicated that the assay did not work well due to much higher estimated concentration of the phenylalanine measured by the bacterial assay than what was measured in urine. Thus, a very high rate of false positive results would be expected in newborn screening. He realized that the journal had accepted this article rather than his, or rather than publishing both articles. In an accompanying editorial concluded that it was therefore premature to advocate routine newborn screening. In a responding letter to the editor, McCready wrote that 50,000 newborns had been satisfactorily screened in Massachusetts with no unduly number of false positive results, and that 8 were found to have markedly increased phenylalanine and confirmed to have PKU. Subsequently, Guthrie's report was published in another pediatric journal, but not until there was a delay of 6 months for a committee report to be received and conclude that the assay was satisfactory for newborn screening. Skip a couple of sentences. Nevertheless, Guthrie was having great difficulty in getting newborn screening for PKU established throughout the US. There was a vigorous opposition from physicians and medical societies that considered routine screening to be socialized medicine and an infringement on the privacy practice of medicine. McCready's published letters were extremely influential in the adoption of newborn screening for PKU by other states. His statement that 9 of 53,000 newborns, 1 in 6,000 were discovered to have PKU was astounding. Here was this totally unexpected incidence, 4 times greater than the 1 in 25,000 assumed prevalence of PKU. It turned out that this presumed incidence of 1 per 6,000 was purely fortuitous. The 10th case of PKU was not discovered by screening in Massachusetts until almost the next 100,000 babies were screened. As McCready once told me, had these 100,000 been the first to be screened, newborn screening for PKU might never have occurred. So you need some luck to get newborn screening going. Opposition to newborn screening for PKU continued. A meeting of consultants to the California State Department of Health concluded that the Guthrie assay required further evaluation and that knowledge of PKU needed to be more complete before screening could be justified. Additional opposition was based on the compulsory nature of newborn screening that was being mandated by laws that were beginning to appear in the late 1963, after the initial law in Massachusetts. In 1964, the House of Delegates of the American Medical Association voted to oppose legislation requiring compulsory testing for phenylketonuria. State medical societies universally continued to oppose mandated screening, the single exception being Massachusetts. Even as late as 1967, when most states had established newborn screening for PKU and had passed laws mandating the screening, opposition to compulsory screening from nationally prominent clinicians and investigators was strongly expressed during a meeting sponsored by the March of Dimes. Most prominent amongst the opposition was Dr. Samuel Besman, a medical researcher who for many years maintained that not only was compulsory newborn screening for PKU unjustified, but that even dietary treatment for PKU was unjustified. So he also had his fair share of opposition, lame excuses, and ridiculous arguments. Very much the same as what we're having in South Africa. Okay, so then there were a lot of other advances, which I'm not going to go into detail. A lot happened in biochemistry, a lot happened in the analytical methodologies, of which I think tandem mass spectrometry is probably the most important. The disease panel expanded, mostly because of tandem mass spectrometry. So initially it was only intoxication disorders, and then later energy deficiency and also complex molecules. And also there were a lot of other developments, like, for example, software developed by the Mayo Clinic, which we use today to assist with the interpretation of these results. Now, one of the things about tandem mass spectrometry is that it enables the identification of numerous compounds in a single run. And the markers that are used in newborn screening are not completely specific. So you end up in a situation where you have a particular target, but because of targeting this particular compound and potentially several other compounds, you're also in a position to diagnose other conditions that do not necessarily qualify for newborn screening. So because of this dilemma, Wilson and Junger published their criteria for screening, which was accepted by the World Health Organization and is still in use today. But it doesn't actually work quite well in this multiplex environment of newborn screening. So the American College of Medical Genetics also published guidelines in 2006 that dictates how one should go about to select a condition for newborn screening. And so I just want to point out that there's a lot of literature on how one goes about to select a condition, and you don't have to guess or come up with suggestions or long arguments of what should be done. One can simply follow the guidelines, and it's going to bring you to the correct answer. And it's also applicable to your environment. So it's not a case of that these guidelines cannot be implemented in South Africa. So because of advances in technology and also in treatments, newborn screening has increased dramatically. So initially it was amino acid disorders, fatty acid oxidation, organic acidurias, galactosemias, endocrine disorders, cystic fibrosis, biotinidase, the hemoglobinopathies, and then came severe combined immunodeficiency, lysosomal storage disorders, adrenal leukodystrophy. Some countries also screen for infectious disorders, then some point of care tests for congenital heart disease and hearing loss. As of late, spinal muscular atrophy as well, and then other conditions have also been considered. And this is the American College of Medical Genetics recommended uniform screening panel. So all states in the United States are advised to screen for these conditions, and these are conditions that has been very thoroughly investigated. And I'm not saying that all of this will be applicable to South Africa. There's also cost and things like that involved. But what I do want to point out is just the growing nature of newborn screening. So you can see here that severe combined immunodeficiency was added in 2010, POMPI in 2015, mucopolysaccharidosis 2016, and then spinal muscular atrophy of and mucopolysaccharidosis type 2 as of late. So there is some guidance in terms of what one should implement in a newborn screening program. The one thing that I think is very interesting and actually creates a lot of opportunities is this thing called precision medicine. Now, precision medicine is the result of very sophisticated diagnostic modalities, but also treatments that have become available. And in many of these instances, if you want to be successful, you need to start the treatment very early on. And so newborn screening or newborn screening conditions are ideal for this next generation treatments, because one, the patients are diagnosed early, and two, is that, at least from a genetic perspective, these conditions are actually very simple. So normally there's just one gene that contains a particular mutation. The product of that gene is not going to be able to serve its function. And so if you want to design a precision treatment, it's very easy to identify the target. So these are the traditional ways in which we treat it. So this is dietary substrate reduction, detoxification, mostly carnitine, cofactor, coenzyme supplementation, proximal enzyme inhibition. This is perhaps a bit more next generation, but NTBC, for example, for type 1 tyrosinemia is an example of this. Dietary supplementation, particularly if you have a biogenesis disorder or a synthesis disorder, like, for example, serine biosynthesis disorders, liver transplantation, and so forth. But the newer treatments that are now becoming available is stem cell transplantation, actually been around for some time already, enzyme replacement therapy, chaperone therapy and proteostasis regulators, advanced substrate reduction therapies, which are definitely now also making its way into the market, therapeutic mRNA that can interfere with expression of particular genes, microbiome alteration, which is also starting to make its way into the market. So here you alter the microbiome to actually assist with the metabolism of some compounds that a particular patient may have difficulty with. And then gene therapy and gene editing is also moving to the forefront. Now, very important here when one applies these therapies is that they're not without risk and they're typically very expensive. So if you do have a genetic diagnosis, you would, in many instances, would need functional confirmation that the disease is in fact present. And so functional studies are becoming very important. So if ever there was a time in history to be a biochemist, it must be now, because our ability to understand and manipulate biochemistry is just on a level, on a much higher level than what it has ever been before. This slide illustrates the mechanism of enzyme replacement therapy and the discoveries around it. So what happens is with enzymes that, or lysosomal enzymes, have a mannose tag, and then there is an enzyme involved, UDP N-acetylglucosamine phosphotransferases, which transfers this group onto the enzyme, and the terminal part is then degraded to leave it with this mannose 6-phosphate receptor. Now, in the Golgi apparatus, enzymes containing this particular tag, let me just point it out here. I think I should use my pointer. So in the Golgi apparatus, enzymes that contains this particular tag are packaged together and then transported to the to the lysosome. The lysosome has a low pH environment, so only enzymes designed to work in the lysosome can actually work in the lysosome. So this is the way in which our bodies are able to specifically target these enzymes for the lysosome. Now, the important discovery here was that these mannose 6-phosphate receptors are also expressed on cell membranes. So if you engineer an enzyme and you tag it with mannose 6-phosphate, it now has a mechanism to be transported across the cell membrane and then transported to the lysosome. And so this is what is illustrated very nicely on this slide. So here, this is the principle of enzyme replacement therapy. So you administer the enzyme, it crosses the cell membrane and then gets channeled to the lysosome where it's supposed to do its function. It's also the mechanism that's used with stem cell therapy. So these cells create active enzyme that can cross the cell membranes and be targeted for the organelle where it's supposed to do its function. The slide also illustrates, of course, gene therapy, where the defective gene is either altered or a dose of normal gene is inserted into the cell, and also illustrates substrate reduction therapy quite nicely. So all of these therapies are currently available on the market and are being exploited in more and more diseases. So, you know, from a scientific perspective, I think the ability to diagnose and identify these patients are quite important, because I think one wants to be a part of the bioeconomy and the new treatment strategies that are evolving as time goes on. So what about exome sequencing as a strategy for newborn screening? Yes, it's certainly in the long run, we're going to see more and more of this. This publication from the California Newborn Screening Program, which is a very well-established program, however, shows that at the moment, it doesn't quite have the sensitivity and specificity required for newborn screening. So yes, in the long run, but not at the moment. High cost, low throughput the ethics surrounding all the incidental findings, the variants of unknown significance, all of those things are still things that needs to be sorted out, but yes, definitely in the long run. I was once in a lecture where the presenter said that if you still have an opinion whether exome sequencing should be done or not, then you should basically just ignore your own opinion, because the market will dictate in future that this needs to be done. How satisfied the market is going to be with the results, I don't know, but I tend to agree with him that this will come in future. So what was the state in 2015? This was the last publication on the state of global newborn screening. So you can see the developed world, North America, universal, expanded programs, Europe, almost universal, mostly expanded, Asia Pacific, increasing, as well as the Middle East and North Africa. You can see the dramatic increase from 2007 to 2015 in terms of established programs. Latin America, very far or very advanced, 15 out of 20 regions, most of them already expanded newborn screening, but then notably not much happening in sub-Saharan Africa. So interestingly, about 140,000 newborns get screened per day around the globe. Okay, so let's just talk a little bit about South Africa. I'm just watching my time. I can speed up things a little bit if needed. So let's just say exploration of the field of inherited metabolic diseases started in the early 1980s by both Northwest University and the University of Cape Town, both of them screening patients, institutionalized patients for phenylketonuria, and both of them finding very low prevalences. And then Jenkins published this paper in 1990, and this paper gives a very, very good summary of developments in genetics in South Africa up to that point in time. So if you're interested in this, I really would encourage you to go and read this paper. In this paper, he summarizes the results of various studies. So there was one in Johannesburg testing for PKU, where they found no cases after 36,000 screens. This was 90% white and then 10% colored Asiatic. In Pretoria, there was also a program, no cases after 40,000 patients, but they did find 11 cases for congenital hypothyroidism. In Cape Town, there was also a screening project for congenital hypothyroidism, 14 cases out of 62 in white patients, and in black patients, they only say that there was a very low, but 23,000 patients screened, which I think this actually created the wrong impression, but anyway. So just something interesting from his publications. Not surprising, therefore, that genetic disorders should be considered to be relatively unimportant by the Black community, whereas the large number of whites, the relative importance of these disorders is clearly apparent. Nevertheless, as increasing number of Black people enjoy improved socioeconomic status and become better educated, they too will expect, and in fact already demand, genetic services. And this is something that Helen Malahab talks a lot about, the epidemiological transition. So as the neonatal mortality rate starts to decrease, the contribution of genetic and congenital disorders become more and more important. And in South Africa, we are certainly here. So a larger and larger investment in non-genetic diseases, let's just call it non-genetic diseases for now, is going to ever produce a smaller and smaller return on investment if you don't start to address the genetic and congenital diseases. Some more screening done in South Africa. This was done by Hitzeroth in 1995. Jenkins actually also refers to this study, but this was at the end of the study, so they screened 57,000 newborns, detected one case of PKU, and it is concluded from this results and other relevant information that newborn screening for PKU and other aminoacidopathies is not cost-effective and justifiable, especially against the background of prevailing demographic conditions and more pressing health priorities in South Africa. This particular screening program was discontinued in 1986. So, you know, the things that we're grappling with was already there in 1986. Of course, you know, PKU is the wrong condition to screen for in South Africa. But a lot more, well, let's just say that the situation for congenital hypothyroidism is very different. So Hitzeroth also did this study where they estimated the incidence to be around about 1 in 4,000, in line with the world figures. There was this study by Libya and Pretorius where they found one case out of just over 1,000 patients screened. And then a very good reference is the study from Kerryhill, where they looked at the incidence in the Cape Peninsula and discovered a rate of around about, again, close to 1 in 4,000 in Black South Africans. So very different from that initial publication saying that it's very low. So it's about the same as in the white population and in line with global estimates. Work was also done on galactosemia. This from Henderson from University of Cape Town, who tested both black and white patients from 1980 to 2001 and found high frequency of this particular mutation in our black population with an estimated incidence of about 1 in 14,000. So certainly worth screening for. This particular variant that they described here is also very amenable to treatment. So, whereas in some areas in the world, galactosemia is not such a great target, early intervention prevents the hepatic complication, but doesn't necessarily prevent the neurological progression. This particular mutation does actually respond very well to treatment. So if there is a place in the world where you should screen for galactosemia, it's here in South Africa. There was some other important publication. Marty Derksen published on isovaleric acidemia. George van der Walt published on glutaric acidemia type 1, found a very high prevalence in Black South Africans. Van Rensburg and colleagues did a very good summary of cystic fibrosis, which I think clarifies a couple of things there. And then Arendt, Heitner, Lane, and Ramsey published on Gaucher, the genetics of our Black population, and also actually showed a very high carrier frequency of Gaucher disease. So after all of this work was completed, we got the 2001 South Africa's Department of Health Human Genetics Policy Guideline. So, and it says the following: specific at-risk population can be screened for particular genetic disorders and birth defects according to provincial needs. Examples include screening for Afrikaner population for familial hypercholesterolemia, individuals of European descent for cystic fibrosis, individuals of Greek and Asian extraction for thalassemia, and those of Ashkenazi Jewish descent for Tay-Sachs disease. However, the psychological disadvantage must be weighed up against the advantages of such screening. Population screening can result in the prevention of birth-affected individuals, as well as prevention of genetic diseases in at-risk individuals. Population screening methods include total at-risk population screening to detect healthy gene carriers and individuals who may benefit from health education, like familial hypercholesterolemia, which for the most part is an autosomal dominant disease with no carriers. Cascade screening, whereby only at-risk consenting relatives of affected individuals are screened. And after all that research, screening of newborns for treatable genetic orders such as phenylketonuria. And you kind of read this and think to yourself, but did I miss another election or something? How did they come up with this, after the research that has been done? But anyway, this is a long time ago, and I'm sure that they also had reasons why they published this. These are some very influential people that were involved. Bradford Thorell, I've had some communication with, very, very influential individual in establishing newborn screening programs around the world. Jennifer Cartwright, a pediatrician that I think is known well by many clinicians. And she used to call me every year to hear what we have diagnosed. And then the late Dr. Mantu Chabalala Simang, who's shown in this photo. Anyway, so now in 2021, we have new guidelines. This has been signed by the Minister of Health. I cut and paste this in here just to show you this, although it's not on their website just yet. The website is still the 2001 guidelines. So, and I just want to read you this part, box 9, progression of newborn examination. Biochemical newborn examination performed by chemical newborn screening on all newborns and stillbirths within 3 to 6 days postnatal. That should be 24 hours. Perform newborn screening for congenital disorders where newborn screening prevents significant and irreversible morbidity and mortality. More studies are needed to determine which congenital disorders must be included in the program. However, an initial screening program should at minimum include congenital hypothyroidism, congenital adrenal hyperplasia, cystic fibrosis, classic galactosemia, glutaric aciduria type 1, and propionic acidemia. Neonates that screen positive needs to be referred for confirmation of diagnostic, genetic counseling, and management. That's looking a lot more promising, and certainly something that we can work with going forward. I'm not going to go into much detail about the newborn screening program at Northwest. I've done this a lot of time, just in bold here, the conditions that we tend to diagnose quite often. Fatty acid oxidation disorders, very few. And if we do diagnose them, it's mostly MADD, which is a secondary newborn screening condition. This is our request from 2010, and you can see initially it was quite a strong growth, and it has then plateaued and even started to decrease a little bit. And this started before COVID, so it's not due to COVID. I think I understand why this is the case, and it's definitely something that we need to address. But it's still very, very small, and I'm keeping it alive because I do believe that in the foreseeable future, we will have a newborn screening program, and then it is going to be of value. And I'm talking about a national newborn screening program. Okay, I still have a little bit of time, so this is quite an important section. So the challenges and the reasons why we don't screen patients in South Africa. And I didn't list all of them, but I just wanted to point out that there are some pathetic and lame excuses, and then there are some real challenges. Some of the lame excuses are not having the infrastructure, don't have the expertise, cannot treat, too rare to be considered, lost to follow up, more important health concerns. I mean, I don't even want to start to discuss this. I really regard this as lame excuses. If this is your excuse, then you should just abandon medicine and health, because then you can't treat any patient, right? But there are some real challenges. One is the political will and policy, and this is now in part being addressed by the new guidelines. I really think that that is a document that is going to enable us to move genetic services, inherited metabolic diseases, and newborn screening forward in future. Disease prevalence and natural history of diseases is always important. I think we have enough information to make a pretty good start, but we will definitely need to collect more information as time goes on. Of course, cost is a consideration. One needs to do the cost analysis, decide what can be added when. One of the great difficulties is early discharge of patients. So we want to screen patients while they're still in hospital. We don't want them to go home and then come back in a day's time to get a newborn screen. But a lot of patients in South Africa are discharged between 6 and 12 hours after birth. And currently, newborn screening is only, well, the guidelines suggest that it should be done from 24 hours. And then there are also some operational challenges that is unique to our continent, like environmental exposure from carts, particularly in summer months. This can be quite an issue. So a couple of years ago, Marie van Reen and myself did a very elementary study of the cost implication of newborn screening and whether it can be justified. So we found in our study that it can be justified. I'm not going to go into the detail, but I can send you the poster if you're interested. But Kerry Hill, in her thesis, also addressed this, and I thought that she actually had a very interesting angle here. So she said that in the Cape Peninsula program in 2004, the cost of finding a patient was 220,000 Rand. So after screening so many and adding up all the costs, and this really is comprehensive costs, it comes to 220,000. She then remarks that it's very, very difficult to calculate the cost of not screening. She did try and do this, but she then suggested something that I thought was very interesting, and that was to compare it to the cost of litigation. So we all know that litigation currently is a huge problem in South Africa. Now, if you have guidelines that suggest that you should do screening for congenital hypothyroidism, for example, if there are enough literature to show that this is important, and you don't do it, and such a case go to court, it would be interesting to see which way it would go. But I can tell you it's going to be a lot higher than 220,000. So if you argue it from this perspective, I think it creates an extra dimension of why the time has come to implement newborn screening in South Africa. Screening at 6 hours after birth, so this is the next project that I want to be involved in, is I do believe that we can screen at 6 hours. This is data from the Mayo Clinic. They collect newborn screening data from all over the world. And because in the States, if patients are admitted to NICU, they get screened very early. So this on the x-axis here is hours, up to 75 hours. And you can see that a lot of patients have been screened between 0 and 20 hours after birth. And you can clearly see that you can distinguish congenital hypothyroidism from normal patients. There was another interesting study from the newborn screening program in California, where they compared samples collected between 12 and 23 hours after birth to 24 to 48 hours. And in fact, overall, the earlier samples missed less cases. I'm just switch on my pointer here. So overall, the earlier cases actually missed, or the earlier samples missed less cases than the samples that were collected during the advised interval. So that's some initial encouraging results that we can screen earlier. Interestingly, when I started to discuss this with colleagues in particularly Scandinavian countries, they became very interested because they tell me that in these countries, patients also go home 6 hours after birth, not because that is policy, but because they discharge themselves. So they're actually also interested in this, and they would want to know if they could screen these patients at 6 hours after birth. So that would be useful information if we can uncover that. Opportunities that is available in South Africa to scientists and clinicians. Our environment does pose some unique challenges. So here's an old slide that I've shown before, but this is just comparing the average biotinidase enzyme activity when the sample was received between 1 and 7 days after collection. And you can see that the enzyme activity decreases by about 10%, much more so for galactose 1-phosphate uryl transferase, the enzyme for classic lactosemia, that decreases from 60% to 42%. On the other hand, if you use a metabolic marker like galactose 1-phosphate, it's very, very stable. So there are some opportunities for scientists and clinicians to design the correct biomarkers for newborn screening in South Africa. So from this perspective, galactose 1-phosphate seems to be the way to go, but then you also have to consider what's going to happen if we start to screen at 6 hours after birth and galactose had not necessarily been introduced sufficiently. So here I'm comparing galactose 1-phosphate concentrations at 1, 2, and 3 days with GALT enzyme analysis. And you can see that GALT is much more stable in the first 3 days comparison to galactose 1-phosphate. So there are some unanswered questions here. You know, should you measure one? Should you measure both? Should it be a reflex test? You know, interesting things that, you know, people can work on. I would just like to advertise again the biobank. We've established this biobank. It's coming along nicely, but I think we need a lot more patients. I also just want to point out again that my intention for this is to be a national resource. So all of the patients on the biobank is available to you for research purposes. You can just contact us and find out what we have. We will, of course, need a protocol and so on. It's not a free for all. You know, I certainly don't want to use these precious samples for projects that is not going to add value to rare disease patients. But the philosophy behind the biobank is certainly to establish collaboration across South Africa. And then lastly, I just want to show you this slide, which is not really applicable to newborn screening, but this for me was just such an eye-opener. So a couple of years ago, we developed some enzyme testing for Sanofi. At the time, these conditions that they were interested in, we didn't diagnose it. And I actually told them that they were not going to diagnose anything, but if they pay for it, I will develop it. And so we developed this enzyme assays, and we did a lot of education. And in the past, you know, the most common conditions that we diagnosed were galactosemia, propionic acidemia, glutaric aciduria type 1, glutaric aciduria type 2. You know, these are the conditions that we diagnosed. Now, all of a sudden, MPS II is the condition that we diagnose the most frequently in our laboratory. It's followed by Gaucher, although a lot of this is historic patients. MPS II are new patients. Galactosemia is still pretty high, but then look at some of the other conditions that's included in the 6-plex enzyme assay. And you want to pick AB, Fabry, Pompe. These we now diagnose more frequently than isovaleric aciduria, glutaric aciduria type 1, and so on. Now they're not more frequent than these established organic and amino acidurias or acidemias, but it's because our clinicians have become very, very well trained. And because of comprehensive training and then also comprehensive testing and confirmation, we've diagnosed many of these patients over the last 2 to 3 years. And this just makes me realize how many other more established inherited metabolic diseases, the organic acidemias and the amino acidemias, are out there that we are not diagnosing at the moment. There must be many, many patients that we are still missing. So there's a lot of work that still needs to be done, and I certainly think that newborn screening can be very critical in diagnosing, identifying and diagnosing these patients, and then providing them with the appropriate therapies. And that I would like to conclude. Just want to say thank you to collaborators and sponsors that have assisted us in many ways over the last 10 years that I've been involved in newborn screening. And then to all of my colleagues at the CHM. One of the best things of working at the CHM is colleagues. I really enjoy working with them. I'd also like to thank, this is actually in the previous slide, but I would definitely want to thank the clinicians and patients that we deal with. Screening and diagnosis of inherited metabolic diseases certainly makes my life worthwhile. So thank you to each and every one of you. Thank you for the engagements, the discussion. I welcome it, and you're welcome to contact me at any stage if you require advice, assistance, or anything. So thank you very much for the opportunity again to Rare Diseases for enabling me to present, and I'm happy to take questions.
Wow, Chris, thank you so much. That was a really nice journey that you took us on this morning. And what piqued my interest was how many of the, the early kind of instigators and those that investigated, like Sagarit and so on, so many of them were prompted to investigate because of affected family members. And I think that very much there's a lot of parallels with that today. I mean, I know a number of people working at Rare Diseases South Africa are there because of our own family members. So it's a sad, but it's a useful thing to happen in some respects. So I see we have a couple of questions on the Q&A. So I'm just going to go through them, Chris. So Sister Bronwyn from Next Biosciences is asking if screening for sickle cell disease could be added to an MBS screening profile.
Yes, I mean, essentially, all of the conditions that I showed you, there are publications with detailed explanation of how to start the screening. And colleagues around the world are also very open to assist. So we've had a lot of colleagues, a lot of help from colleagues in the Netherlands and the Mayo Clinic in particular. So any condition can be added, but of course it comes at a cost. And I think the aim of the newborn screening program should be larger coverage at this stage than rather than including more diseases. I think the other aim that for me is quite important is establishing reflex testing. So ideally we want to make, so traditionally newborn screening is seen as a screening test, and then there needs to be confirmatory testing. But some labs, and this is where Mayo is really at the forefront, are doing confirmatory testing on the same spot. And this is really where I want to go as well. So you send in a spot, there's no repeat, there's no confirmatory testing. If you have the diagnosis, it gets made there and then. And so that's definitely where I'd rather want to move than, for example, adding sickle cell disease. Now, a lot of African countries have asked me about the possibility to add sickle cell disease because of the high prevalence there. And I tell them, yes, as soon as you send me 20 samples a month, I'll add it. And so far, nobody has achieved that. So we're not adding it just yet. But ideally, what one wants is an advisory panel. I mean, this is the way in which the States is going. And you have different people on the panel. So you have clinicians, scientists, patient advocates, and so on. that scrutinizes the available data according to a procedure like the ACMG has established, and then decide whether a condition should be included. And then typically it's included as a for a trial period for a couple of years, and after which a decision gets made. For example, Krabbe disease was included in New York State screening program now for a couple of years. And they've diagnosed the patients, but the early intervention, the word is still out whether it makes a difference, so whether Krabbe disease should be on a screening panel at this stage is still up for debate. So it's not been included in the recommended uniform screening panel. But yeah, these things, they're all debates that I think should be discussed by different people with different background, different interests, different stakeholders. That's really the word that I'm looking for. I can actually see the questions if you like. I can just go through them myself.
Okay, go for it. There's one that on the chat as well from Amanda.
Oh, okay. I'm just going to go through the question and answer first. What's the potential role of single cell sequencing for inborn errors of metabolism? Well, at this stage, we collect a dried blood spot. Of course, that could change in future, which provides enough genetic information to do an entire exome. So there are a number of projects running currently in the world where whole exome sequencing is investigated as a primary newborn screening tool. And we're waiting for the data from that to see what has come of that and, where that will go. But like I said, whole exome sequencing is coming. In what capacity it will be rolled out, I'm not sure. Whether it will be confirmatory or whether it will be primary and biochemical will be confirmatory. I don't see whole exome sequencing as replacing the biochemical test, well, not for quite a few years, maybe in future. The thing about newborn screening is when you start to screen for a condition, the incidence typically increases quite a bit. So the classic condition for this is 3-MCC, 3-methylcrotonil-CoA carboxylase deficiency. So this used to be an extremely rare condition. And then when newborn screening was started, it all of a sudden became very common. And what was clear is that there are patients with the biochemical phenotype and the genetics that never presents clinically. Now, if you start to implement whole exome sequencing, you're going to have this times 100, right? So you would need biochemical confirmation and also in some way come up with functional studies that is going to be able to tell you that what you're seeing on a genetic level is going to translate into a clinical phenotype. So there's a lot of work that needs to be done, but yes, I do think it's coming. Then there's a question again from Bronwyn. Would adding gold to the NBS sample tested, which shows an elevated galactose 1-phosphate, be possible at NBS lab at NW instead of requesting this formally via the PAF labs and testing done at the NHLS? Yes, we are investigating it at the moment. So I do foresee that in the next 6 months or so, we will implement it. The question really is just, should this be the primary screening test? And we accept that there's some sample degradation. The CLIA software that I've shown you can actually, to some extent, assist in identifying samples that were subjected to degradation. So even though the samples do get degraded, you can still use them to interpret the results. And it doesn't have the drawback that the patient must have been exposed to a lactose-containing formula. Or should we go the galactose 1-phosphate route as the primary screening test? But then we need to think about the coming days where we would want to screen at 6 hours and where the diagnostic accuracy of the test may not be good enough. So there are some unanswered questions there that still needs to be resolved. So Bronwyn has a lot of questions. Doing the confirmatory testing on the DBS sample would be amazing. It is so challenging to get confirmatory samples collected and tested, and the cost of these are often challenged to parents. We're doing these on DBS card reduced costs. Yes, absolutely. That's why I'm interested in it. One thing that's just difficult is the politics, right? So, we can actually quite quickly start to introduce confirmatory tests, but there are now a selected number of samples that needs confirmatory testing, and the cost of that confirmatory testing ideally must be covered by the whole program. So instead of charging someone 2,000-3,000 for a confirmatory test, you rather increase the cost of the program by R1 or something like that. But yeah, it's very, very difficult to increase the cost of a test, so that's why I think, you know, an advisory board, and so with representation from medical aids where data can be shown, where they can understand the implications of these things, would be very, very beneficial going forward. Then just in the chat, I see there's quite a few things there. So Professor Krause is saying, hi, Chris, thank you for your excellent talk. Just wondering how confirmatory dosing occurs biochemical and or genetically, particularly as it gets rolled out. So there are, again, very clear guidelines on what kind of testing should be done, whether it should be biochemical or genetic. And of course, both of them has got their advantages and disadvantages. If I can just maybe talk about the more traditional disorders, the amino acidemias and the organic acidemias typically is biochemical confirmation. But the fatty acid oxidation disorders, we know that they don't always present biochemically. So there one tends to go more for genetic confirmation. It's also a case of what is available in the country. Then, for example, one condition that I find very challenging, cystic fibrosis. Most of the world will do genetic confirmation, but like Bronwyn has pointed out, it's expensive. So sometimes we're left with having to do sweat tests at a time when it can actually be done. So again, you know, there's a need for a bit of development there and guidance in terms of how the newborn screening should address these conditions in the most effective way possible. Okay, I think I've now pretty much answered everything, Helen, unless you can still see something.
No, I think you're right. I think that's all done. And I think just following on to what you've said, a lot of you know, responses, to me, it really indicates the need for health economic evaluation of these, because we first have to quantify the burden of disease, but then we have to also highlight, you know, what are the costs, not just monetary, but we also have to show the health outcomes. And it's that evidence-based information that we need to actually leverage to, you know, increase, you know, the availability and offerings of these types of services.
Yeah, look, I think in some instances, like congenital hypothyroidism, everything is actually there. I mean, there's local studies, there's been international studies. The treatment is low cost, is extremely effective. There is just no excuse why we are not screening these children. I mean, the Cape Peninsula have been screening for a long time using cord blood. You know, yeah, I can't think of a reason why we're not screening for congenital hypothyroidism. Of course, it is a condition with that produces quite a few false positives. So I think, you know, you need some expertise in terms of the follow-up of these patients, but that can be established quite easily, I think. And once one has that established, you know, then one can go more systematically through some of the other conditions. The thing is also is that, you know, once you have one condition established, then it just becomes so much easier to add another condition, because all of the logistics costs and the sample logging, transport, all of those things are already covered, right? So you're now only left with the cost of testing and the confirmatory tests, which all of a sudden it becomes, the cost of screening becomes a lot cheaper. And then if you add the next condition, it's even cheaper, and the next one is even cheaper. So I think, you know, congenital hypothyroidism is where we start. And then from there on, we start to systematically work through them from all angles, economics, benefit. I mean, like I said, you know, if you follow the ACMG guidelines, in the United States, those guidelines may dictate that you should screen for MPS 1. I think in South Africa, the same guidelines may not come to the same conclusion, just because of the differences in our economies. But at least, you know, it gives a very solid foundation from which to argue this. And also it opens it up to for discussion. You know, I think some of these expensive therapies do not need to be so expensive. We just need to be well organized and well grouped, make a case to developers, and, you know what, potentially also develop our own therapies. I know that there's one institution that's looking at enzyme replacement therapy. You know, if we have such a big burden in MPS 2, then, you know, perhaps that's where we should develop a therapy in South Africa. We certainly have the expertise, the infrastructure, and the ability to do it. We just need to come together and actually do it.
Well, on that note, which I think you've really summed up so nicely, and, you know, in a positive note as well. So thank you very much, Chris, for your presentation today. I think it's a lot of food for thought and eye-opening in many respects. And thank you to everybody else for joining us. We had nearly 60 participants online today, which is fantastic. If anybody does have further follow-up questions, I'm sure that Chris won't mind if you don't contact him directly, or you can alternatively contact myself or other colleagues at Rare Diseases South Africa. So here's looking to the future and to, you know, making it a reality in South Africa for newborn screening.
Thank you, Helen. And
So
thank you everyone for listening.
Thanks, everybody. And we'll catch you next time for our final Rare Research Seminar of the year, which is planned for, I think it's September. Sorry, we're in September, late October, early November, but we'll be sending out information about that soon. Thanks so much, everybody, and have a good rest of the day. Bye.
Thank you. Bye-bye.